All right, guys, just wanted to make a little quick video to summarize what we kind of rush at the end of class here today. Approximating the binomial using the normal distribution. Well, let's go back to the question, just reiterate what happened here. Suppose we have a population, right, and of people, and we're talking about the population percentage, right? I should probably add that in. The population percentage of lefties is approximately 13%, or that P is equal to 0.13. And suppose we take a sample of 3,000 people, or that N is equal to 3,000. So we got N equal to 3,000 and P equal to 0.13. Well, is this binomial? I mean, there's a four-system check. So one, does the population stay constant? You know, is the population 13% as I grab each person? Yep, it stays constant. Someone's either left-handed or not left-handed. Correct. Whether somebody is left-handed is independent of the next person. Check. And I believe that 3,000 is less than 10% of the population of all people. We could say in the United States for this question. Good. So this is definitely binomial. Let's move on. Since this is binomial, I can say that my mean is equal to N times P. So 3,000 times 0.13 is equal to 390. So I would expect that the amount of left-handed people in a sample of 3,000 is approximately 390 people, with a standard deviation of the square root of 3,000, right, NPQ as I call it, whoops, and I just noticed that I have 1 minus Q, that should be 1 minus P, where Q is equal to 1 minus P. I'm always in the habit of just writing the standard deviation as the square root of NPQ. It's just easier and neater. So that's 3,000 times 0.13 times 0.87, which is equal to approximately 18.42, right? And that's people and people. Those are my units. So that's my mean and standard deviation. All right, well, what could I do with that? Well, it goes a little something like this. If your N, right, if the size of your sample is large enough and X is binomial, that follows a binomial distribution of NP, where X is the variable of choice, our random variable, which is the number of left-handed people, then X is approximately normal, where it follows a mean of N times P, that's our formula for getting the mean of a binomial, and a standard deviation of course, the square root of NP times 1 minus P. So, can we use this? Sure. We can use this for our problem at hand. What's the one additional check? What's large? Large enough is denoted by N times P, our expected number of successes, because P is the rate of success, or proportion of success. So N times P is greater than or equal to 10, which for our problem, N times P was 390, bigger than or equal to 10, check. And then N times Q greater than or equal to 10, or this is the number of failures. What we want to say is we expect at least 10 successes and 10 failures in our sample. So if you gather a sample and you have that expectation of at least 10 of each, then that's what we consider to be large enough. How many failures do we expect? We expect 0.87, right? 0.87 times 3,000, right? This was 0.13 times 3,000. But we had already had that arithmetic taken care of. 0.87 times 3,000 is 2610, and that's greater than or equal to 10. Check. So we're good to go. We have a binomial that follows this distribution, and we certainly have a large enough sample. And of course, when you take your NP and NQ, these should add up to your sample size of 3,000. All right, let's move on. So for our lefty problem, if we're looking for the probability of X being less than or equal to 400, or what's the likelihood of having 400 or fewer people that are left-handed out of 3,000, This is a CDF problem because we're less than or equal to, so we go into the binomial function, CDF, for n of 3,000, probability of 13, and an x value of 400. You press enter on your calculator, you get approximately 0.7172. And all we're saying now is that we can also use the normal distribution function on our calculator to use the normal model to approximate the same answer. So where do we go? We go to our norm CDF function in our calculator. We're going to enter our lower bound, upper bound, mean, and standard deviation. Well, the lower bound, if we're looking for less than or equal to 400, even though 0 is the lowest we could get here, we're just going to go with what we know and love, negative 10 to the 99, all the way to 400. Our mean that we've already calculated is n times p. Remember, our mean is n times p, so that's going to be 390 and a standard deviation of 8.42. And when you hit enter in your calculator, you're going to get an answer of 0.7064. Now again, is that exactly the same answer? No. This is the approximation of that answer. Why would we use this alternative method? Well, prior to calculators and computers, this would be a faster, more efficient manner to approximate an answer that might take copious amounts of hours to calculate out by hand. So we needed a shortcut. Your calculator can handle this, so would we actually use the norm approximation? I don't think so. At least not for this question. But the question was raised, well, how about the opposite version? What about the probability of, in a sample of 3,000, the likelihood of having 400 or more lefties? Now, when we approach this from a binomial standpoint, that's the same as saying 1 minus the probability of x being less than or equal to 399. If we want 400 or more, what we don't want is 399 or less. And the reason why we have to go with that less than or equal to is because that's what the binomial CDF function accomplishes. But as we all saw in class today, the pitfall, sometimes we actually forget to subtract it from 1. So 1 minus binomial CDF, right? And then we have our NPX, and you get an answer of 0.3013. For the normal model, the probability of x being greater than or equal to 400 doesn't require any kind of fancy subtracting from 1. We just go right in, norm CDF. Our lower bound then is going to be 400. 10 to the 99 is our upper bound. Our mean is going to be still 390 and 18.42. Squeeze that in there for our standard deviation. And what do we get for an answer? I get 0.2936. And again, not too far off from our original answer. Again, this is an approximation. So hopefully this clears up the how to use the normal model to approximate a binomial. And remember, the key piece is you have to expect at least, sorry, I cut myself off there, 10 successes. P is our probability of success. Right, so, and 10 failures. This is a must before you use the normal model. If you don't expect this, then it's not appropriate to approximate the binomial with the normal if you don't have these two conditions. Just a couple more things. With respect to regression, why is your model appropriate? Well, there's a couple of things we want you to touch on here. We want you to talk about the correlation coefficient being strong, perhaps that there are no outliers affecting the value of the correlation coefficient, right? No artificially strong correlations, outliers. We want to talk about that resids plot. It has a pretty decent random scatter. So those are good reasons why the model is appropriate. Hopefully both variables are quantitative, but that's a basic given. As far as random variables goes, random variables. Now I'm just getting really sloppy. When we talk about, the sum of two random variables, x plus y, maybe we're talking about the mean of x plus y, and that's standard deviation of x plus y, and then we follow that up with a probability statement, like what's the probability of the values of x plus y being, greater or less than of some value. We would probably hint that it follows a normal model. Just remember that after you calculate the mean and the standard deviation of those things, of those items, you have a normal model with a mean and standard deviation of their sums, and you could use the normal model to answer probability questions. So don't get nervous about questions like that. All right, I think that's enough of my blather. Have a good night.